The objective of the practice is to conduct a Gemini test with a Gemini specimen, and when quenching the piece, to obtain the different cardinalities of the steel, in this case 1018, at the different distance of the Gemini test, and determine why the hardness change. So for this practice, we have this piece of Gemini specimen of stipulated length and dimensions, and we need to put it in a solution of copper sulfate for 5 seconds. After we've done that, we need to clean it with dry air and put it in the oven above the temperature of the ACM line for 30 minutes. Once we've done that, we have to take out the piece and put it in the Gemini equipment for 10 minutes to cool down. As you can see, our piece is cooling down. Our material is still 1018. And after we've done that, we take out the piece and we quench it in water so that we can take it.
¿Sabes? Fotos, güey. Fotos. A su madre.
Ese calor no es nada.
Ay.
As you can see in the video, to obtain the Rockwell C harness, we have to put our Gemini specimen in a special device that helps us to make indentations, moving our piece in an axis. So once we obtain our harness for one point, we just move our device and make the other point, moving each time 1/16 of an inch.
For the Gemini test, we have to use this water quenching device, in which the water they provide with a pump, a stream of water, which we can control with a pump that is under. So the water is passing through an orifice here of 0.5 inches. So we have to put our Gemini specimen. So they have a diameter of 1 inch. So we introduce here, and they have a little space of 0.5 inches, so the water can hit the Gemini specimen. So they start to undercool all the piece and have like different properties of the quenching in the piece, so we can
We found out that the lower percentage of carbon our steel has, the higher hardenability it will have. The steels that have worst hardenability are alloy steels.
In order to define some terms, we must define their hardenability, which is the facility to obtain martensite from austenite. Then the severity of the temper is related to the cooling velocity and the temper process, and it can vary from accordingly to the tempering medium or water or oil. The real critical diameter is where the 50% of the martensite is formed, in the center of the piece, and the ideal critical diameter is the same, but the difference is that this ideal has an infinite percent of heat absorption. The correct tempering is when the piece it's totally in austenite phase and changes to finally the perfect tempering is when it cools down in a way the same structure stabilizes and becomes martensite.
In order to find the critical idea of diameter for our 1018 steel, we can use two methods. Method number one is with the formula, and method number two is graphically, this graphic. So first, we have to define the percentage of carbon that our steel has, and here we make an approximation to 20%, even though it's 1018, and then we have to define the grain size of 1018 steel, and from previous experiments in previous courses, we got to the conclusion, we found out that grain size is 6. So we locate 2 here, and then with the curve of 6, when it touches number 2, we draw a straight line, and we found out it's 0.70. In order to provide the cooling rate in a 0.25 millimeter in the Germany scale, first we have to convert 25 millimeter in inches, and that will give us 0.9884 inches, and in that specific number we get the approximate velocity of cooling is 5 degrees per second.
The influence of the austenitic grain size is that the grain size in the austenite and the martensite is the same size, and the grain size reduced increases the mechanical resistance and affects the martensite.
Okay, so as we make our indentations, we started from this end of the piece, and we advanced 1/16 of an inch, and made a Rockwell C test each diameter. Now, as you can see,
From our test, we obtained the values of Rockwell C for our Gemini specimen, but since we could only obtain in theory the values from Rockwell B, we made a conversion with the table shown from Rockwell C to Rockwell B. So we can see in our new table with Rockwell B values how at the beginning the hardness starts at 89 and it starts to go up, and in the middle it fluctuates and stays in a constant at the end at 31. Now, as we see the second table, the one we obtained from investigation, we can see that the behavior of our table is similar to this one. No sé qué más decir.
No, pues faltamos nosotros tres. No
It can be noticed that the 1018 steel behaves in a different manner than the steel shown in the table, as it starts from a low point of hardness and it starts going up, different in comparison with the other steels that start with more hardness and starts decreasing.
Well, in this practice, I learned how to do the tempering process and how it affects the fact that in our probe it was cooled with water just in the part above, so that affected the composition and the formation of martensite along the probe. And I also actually discovered and learned that austenite, when submitted to a certain tempering process, transforms into martensite, and also how the hardenability depends on the tempering process and the percentage of carbon.
In this practice, I learned the Gemini test and the different temperings. Also, I learned that the cooling rate depends on how we put the water or oil in each case, and how this affects in the hardening of the probe in each of the stages. Also, I think this is a really good practice because I could see and calculate some of the grain size and also apply the knowledge to other courses. So I think it's really cool.
My conclusion for this practice is that when working with steels, in this case, the quenching process is as important as the constitution of the material, because as we could see in the Jomini test, our specimen had different hardness in each distance from the quenching end that was in contact with the water, with the outlet water of the Jomini device, than when getting closer to the end of the test of the specimen. So if you have a certain property that you want to obtain for certain application, you need to take into consideration the quenching time and the contact of the piece with the hot water or the medium.
In conclusion, I find very interesting all the concepts that we learn in this practice, because we find that the steel has different like layers of quenching, because these give different temperatures. So with this practice I saw how the properties change from the time and the temperature that they undercool the piece. So for an application in the industry, this is very important, because you want to apply different applications, so you have to know all the time and the temperature that you have to apply to the quenching in the steel, and apply all the properties that you want to have, and use it in your company.